Good afternoon, everybody. This is week 1, lecture 3. In this lecture, we are going to continue with the concept of functions. We're going to look at quadratic functions as well as cubic functions. Basically, what we're going to do today is we're going to apply most of the ideas that we had in the last 2 lectures. We're going to look at total cost function, then try to do some computations. Then I will then introduce you to basic calculus. We're going to look at the rules of differentiation, the concept of derivatives. We also look at rational functions. The reason why we're going to do rational functions is because most of the models that we're going to be using, especially in consumer demand theory, producer theory, and the concept of the equilibrium, perfect competition, oligopolistic markets, these all use some rational functions. So we're going to look at rational functions in this particular lecture, and we're also going to start with the rules of differentiation. And there are so many rules of differentiation. We need that because when we move on to the concept of optimization, we want to know which rule of differentiation we're going to use to find the optimal values. We want to know which method we're going to use to obtain the outputs that maximizes profit, or the profit maximizing level of output. So you will only know this one if you have some basic idea of differentiation. You know what the basic rules of differentiation are, and we're going to be using this one in the concepts of profit maximization and price discrimination. So let's go ahead and get started. We're going to start with some economic applications here. In the last lecture, we look at the quadratic total cost function as well as the cubic total cost function. And we stated that the quadratic function is of degree 2, is a polynomial of degree 2. And if we try to apply this one in economics, we notice that the total cost function becomes quadratic if there is diminishing returns to the variable factor. So if there is diminishing returns to the variable factor, then the total cost function becomes quadratic. The cubic total cost functions have an area of increasing returns. As I said yesterday, it has an area of increasing returns. And then where the the graph starts to rise and then attains a maximum and then tapers off. The point where it tapers off represents constant returns to scale. And the point where the graph starts to rise again represents decreasing returns. So in a cubic total cost function, there is an area of increasing returns and then another area of constant returns and then decreasing returns. So where the graph is increasing, where the graph is rising, after it tapers off, represents the region of decreasing returns. So the point where the graph starts to increase before it tapers off represents the increase in returns. Now, if you look at the graph here, the horizontal line is the fixed cost. The fixed cost, which is A. And then you have the variable cost, which is given as BQ plus CQ squared plus DQ cubed. So we have the fixed cost and then the variable cost for the cubic total cost function here. So you see the first region represents the region of increasing returns, and then the second region represents the region of constant returns, and then the third one represents the region of decreasing returns. We are going to discuss this one in detail when we deal with the theory of production, where you have only one input, which is labor, and what happens when you continue to increase the number of employees, what happens to the total return, or what happens to the marginal return. So we're going to look at that one when we deal with the theory of production. So for the meantime, let's just have some of these basic ideas, and then we're going to build from this one. Now, let's look at power and rational functions. A power function is just a function that expresses f of x equals to x to the power a. That is the independent variable is raised to a power. It's raised to a power. The power there is a constant, and that constant takes different values. It could be -1. It could be 1/2, which is half. And if you look at this particular power function, y equals to x to the half. Now, this represents one law in economics. One law in economics that we're going to talk about later on. And to give you just a clue here, this represents the law of what? Diminishing returns. So we're going to be looking at this one later on when we deal with production. And also you have a situation where x equals to y equals to x to the -1. That is 1/x. Again, for that particular function, it is the function is asymptotic to both the vertical axis as well as the horizontal axis. Now, when I say it is asymptotic, now if you have a power function which is given as y equals x to the -1, y equals x to the -1. Remember, x to the -1 is the same as what? is the same as 1 over x, right? Okay, so x to the minus 1 is the same as 1 over x. So if you have a function of the form y equals to x to the minus 1 is the same as 1 over x, then the graph actually is on the first, because if we draw a plane Cartesian plane, we draw the 4 coordinates there. We have the first, the second, the third, and then the fourth quadrant. You will see the graph looks like a curve. It looks like a curve, but it does not touch the x as well as the y-axis. So we're going to take a look at those types of functions later on. So, but this typical example here, y equals to x to the half, is given as this function, this red line. So we have y on the vertical axis and then x on the horizontal axis. So we'll be using this one in due course as we move on. So let's forge ahead. Now, we talk about a rational function here. Sometimes you have the ratio of two polynomials, right? So a rational function is just the ratio of two polynomials, which is of the form f of x equals ax over bx. Now remember, ax is a polynomial and then bx is also a polynomial. So if we take the ratio of these two polynomials, then we have a rational function. Now, given as this, y equals f of x equals to x squared minus 9x plus 20 over x minus 4. Remember, the numerator here, x squared minus 9x plus 20, is a quadratic equation. It's a quadratic equation. It is quadratic in the sense that the degree of polynomial there is 2. And then x minus 4, which is the denominator hit there, is a linear function. It is also a polynomial of degree 1 because x is raised to the power 1. Remember, a variable raised to the power 1 is the variable itself, right? A variable raised to the power 1 is the variable itself. A variable raised to the power 0 is 1. A variable raised to the power 0 is 1, or anything raised to the power 0 is 1. A to the 0 is 1, b to the 0 is 1, x to the 0 is 1. X raised to the power 0 is always equals to 1. Now, I want you to take note of that one because when we're going to be saying those things quite often as we move along. So just take note of that. X raised to the power 0 is equals to 1. The value of that is equals to 1, right? Okay, so now a typical polynomial here is also given as v cubed plus v squared minus 4v minus 4. Now remember, this numerator is a cubic function. It is a cubic function of degree 3. So because the value, the variable v here with the highest power has a value equals to 3. So that one is a cubic function of degree 3. And the denominator is a quadratic function, and it is a quadratic function of degree 2. So it's also a polynomial. So if we look at both the numerator and the denominator here, both of them are polynomials. So the rational function, therefore, is just a ratio of two different polynomials. It's the ratio of two different polynomials. So we have the numerator, which is a polynomial, and then the denominator is also a polynomial. So if we take the ratio of those two, then it becomes a rational function, right? Now, let's move on to transcendental functions. What are transcendental functions? These are non-algebraic functions. Remember, we talked about this one in week 1 lecture 2, right? Or week 1 lecture 1. We talked about transcendental functions. This is a form of a non-algebraic function. Sometimes it is expressed as an exponential function. Now, if you look at the first equation here, y equals to b to the x is an exponential function where b is a constant. And the transcendental function is also expressed as a logarithmic function. So, the logarithmic form of this transcendental function is given as what? Y equals to ln x. So, this is a logarithmic function. Or in other words, we say y equals to log x. Y equals to log x is a logarithmic function, right? Now, if we take the log of the independent variable and equate that to y, then that function becomes a logarithmic function. Now, if we take a constant and then raise it to the power x, then equate that to y, that becomes an exponential function. Now, an exponential function can also be represented as y equals to e to the x or y equals to e to the ax, right? So these two types of functions, the exponential function and the logarithmic function, are referred to as transcendental functions. They are referred to as transcendental functions. We're going to be using these ones. We're going to come across these ones when we start to do the Marshallian demand concepts and the indirect utility function and the Ixian demand function. So when we start to do those functions next week, the analysis of consumer behavior next week, I believe you guys will be able to grasp this concept. Now we have the tangency condition. Now, what is a tangent? A tangent is just refers to the point at which, let's say, a given line touches a curve without crossing each other. Now, sometimes you will have this function, this curve, tangential to straight line. So that point of tangency is referred to as a tangent condition. So the point of tangency between the graphical function in red and the blue straight line is point Q. So the two graphs do not cross each other. If they do cross, then it is not a tangency condition. If the red line crosses the blue line at point Q, then it is not a tangency condition because the line crosses, the graph crosses the line. So the graph has to be the red curve has to be tangential to the blue line. In other words, it has to touch the blue line at a particular point. The point where the red line touches the blue line at a point is referred to as a tangent. It's referred to as a tangent. It is tangential to the blue line. Now, we're going to look at this condition when we look at the budget constraint. See the indifference curve tangential to the budget constraint. And the point where the indifference curve touches the budget line is the point of equilibrium. So that is the point where we have the optimal bundle of the two goods that are consumed by the consumer. So the consumer consumes the optimal bundles. That is the point where the indifference curve is tangential to the budget line. So that is the point of equilibrium. So that is the point at which the consumer is going to buy the two goods. So the consumer is going to consume the goods at a point where the indifference curve is tangential to the budget line. And the budget line, as we shall see later on, is a straight line. And the indifference curve is convex to the origin. It is convex to the origin, and the point where it touches the budget line is a point of equilibrium of the consumer. Now let's move on to basic calculus here. We are not going to into the nitty-gritties, going to the difficult aspects of calculus. We're not going to do trigonometric ratios here. We're not going to do all those ones, maybe the concept of limit. We're not going to be doing those ones. We leave those ones for the mathematician. But let's look at some basic rules of differentiation here. Now, in economics, we use the concept of derivatives to solve what? Unconstrained and constraint optimization problem. Now, you remember I told you that economics is a study of what? Constraint choice. It's a study choice. How we make choice in the face of scarcity of resources. The resources at our disposal are scarce. And the means of having those ones, maybe the goods that we want, our wants are numerous. We have unlimited needs. We have unlimited wants. But the resources at our disposal are limited. So this is why you have to make a choice. You have to make a choice between going to college and getting a job. Now, if you decide to go to college, then it means you are going to forgo maybe the pay that you're going to get when you take up a job. So I know some of you are working, but sometimes you have to do your schoolwork at the same time. So if you decide to do your schoolwork most of the time and work less, then the cost of you studying is not the amount you spend maybe reading your books. It is what? Maybe the income that you are losing, because you're not working. Because if you decide to study more, that means you're going to devote a lot of time to reading. So that means you're not going to be spending time maybe in the office to do some work and get some money. So the cost of that study is not the amount that you spend reading your books or maybe doing assignments, maybe taking tests, or maybe writing research papers. The cost of that is the amount of money that you could have earned by maybe working more. So that is the cost. So in everyday life, everybody is faced with this problem. We have unlimited wants and then limited resources at our disposal. So because of this, that is why people study. That is the reason why we study economics. Because we want to make the best use of what we have at our disposal. So making the best use here means you have to make a choice. You have to do without, you have to trade off certain things in order to get the things that you want. So this brings us to the concept of optimization. So the rules of differentiation here, we're going to be using these rules in order to obtain optimal values. So let's go ahead and get started here. Now, the first rule of differentiation is just a general rule, which says that if you have y equals to x to the power n, then the y dx is just what? N x to the power n minus 1. Now remember what is happening here is if we have y equals to x to the n and we want to differentiate this function, remember the y dx is just the same as what? D f of x dx, right? Now if we say f of x equals to x to the n, right? It's just the same as what? Df of x dx, which is equals to that. So in order to differentiate this function, what do we do? The general rule, if you have y equals to x to the power n. Now, x to the power n is a power function, right? Now, we talked about this power function earlier, right? X is raised to the power n. N there is a maybe a constant, right? So what do we do here to differentiate y? To find the derivative. Now, when we say differentiate, means you are finding what? The derivative of that particular function. You're trying to get the derivative of that function. Now, the derivative here is referred to as dy dx. That is the change in y over the change in y over change in x, right? So that is the derivative here. So what we do here as a general rule, we are going to take the power. Now you see y equals to x to the power n, right? We are going to take this power n and multiply the entire x to the power n by that value n. Have you seen? So if we multiply x to the n by this n, it's going to be n x to the power n. But the general rule of differentiation is that the first rule says that if you have y equals to x to the power n, you always have to subtract 1 from the power. After multiplying the power by the whole function, then you have to subtract 1. That is a general rule. That is a general rule. So now let's look at this one. You multiply the independent variable by its exponent, n. That is what we did, right? And then the exponent is n, and we multiply x to the power n by the exponent n. That becomes nx to the power n. But then you have to subtract 1 from that exponent. We don't just leave the exponent like that. We have to subtract 1. So if you do that, then you have differentiated this function with respect to x. So basically, that is the rule, and that is what we're going to be using. I want you to understand this very well. Please, I want you to understand this very, very well. Because last year, so many people made a lot of mistakes, and I don't know whether they did not understand. But basically, if you are able to understand this simple one, I guarantee you'll be able to do everything. All the problems that we're going to be doing in consumer demand theory, profit maximization, oligopolistic theory, game theory, etc., etc. You'll be able to do all those ones. It is just try to grasp this concept. Try to know the general rule of differentiation here. That if I have y equals to x to the n, and I want to find the derivative of that with respect to n, all I need to do is to multiply my independent variable. Remember, y equals to x to the power n. Y is dependent, and then x is independent, right? So I have to multiply that independent variable by the exponent, and that exponent is n, right? I have to multiply that by n, and then finally I subtract 1 from the exponent, and that gives me my derivative. So if I am able to understand this one, then I will know exactly what to do with the others. So basically, this is what you will need to know. Okay? Now, so let's try to solve one typical example here. Now, find the derivative of the function y equals to 3x squared. Now, remember, y equals to 3x squared. Now, 3x squared, x there is the independent variable, and then y is the dependent variable, right? But this x is raised to the power what? 2, right? So what did we say? We said that if we want to find the derivative of this function, or want to find the differential of this function with respect to x, that is dy dx, what we do here, we multiply the exponent, which is 2, by this whole term, 3x, right? And then we have 3, then times 2x raised to the power 2, right? But we also need to subtract 1 from that power. Have you seen? So 2 minus 1 is just 1, right? And so 3 times 2 is 6. So we have 6x. You got it? Now, in fact, for simplicity here, if you have 3 equals to x, y equals to 3x squared, all you need to do is to separate that constant term, the coefficient of x. Just separate it from the variable x to the power 2, right? So you can take 3 out of the equation. Take it out of the equation, right? Now just try to differentiate x to the power 2. Now the x to the power 2 there, you want to differentiate that, right? You take the exponent, which is 2, and then you multiply that by x, and then raise to the power 2 again, then you subtract 1 from that. You say minus 1. That is the basic rule. You need to understand that. If you understand that, you'll be able to do everything, anything that you can think about. So this is 3 multiplied by x multiplied by 2x raised to the power 2 minus 1, right? And 2 minus 1 is just 1, right? So 2 minus 1 is 1. Remember, a variable raised to the power 1 is the variable itself. No, we don't need to say x to the power 1. No, just say x, right? It's the same as x to the power 1. You got it? So 3 times 2 there gives us 6x. That is the solution to this problem. So if somebody asks you to differentiate y equals to 3x squared, that is what you need to do. As easy as that. So remember, we have now used that general rule of differentiation to find the derivative of this simple function. And we're going to be doing this one every time. Every time we're going to be doing this one. Now, let's look at one typical economic application. Now, consider the revenue which is RQ, and the cost which is CQ, functions of a farm producing pencils. Now, suppose the revenue function is given as 1,200Q minus 2Q squared. Now, remember, what is the revenue here? How do you get the revenue, the total revenue? The total revenue is what? It's just the price multiplied by the quantity. That is simple, right? It is just the price multiplied by the quantity. Now, if the producer is producing like X amount of Colgate or X amount of pencil, and let's say one particular pencil costs maybe the price pencil is $5, right? If the price is $5, then the revenue there is 5 multiplied by X, which is 5X, right? So if, let's say, the producer produces 1,000 pencils, and then the price of each pencil is 5. So to get the revenue, how much you get? The receipt. Total revenue is what? The price, which is 5 times 1,000. That gives us 5,000. So that's how you get the revenue. So that's the same thing we do here to get this revenue equation, right? So for this revenue equation, we have RQ equals 1,200Q minus 2Q squared. And then the cost function there is what? Q cubed minus 61.25Q squared plus 1528.5Q plus 2,000, right? Now, we are to derive the profit function by Q. We are to derive the profit function by Q. That's the first thing we have to do. And then what is the by the Q? That is what is derivative of the profit function with respect to Q. So how do you get the profit function here? Now, the profit here is what? Is the total revenue minus the total cost. It's simple. Now, if I spend like $100 to make pencils, right? I buy some raw materials to make pencils, and then it costs me like $100. And then I try to be like the factory, which cost me like maybe $10 to start to set up. So I need to add that fixed cost to my variable cost, right? So if I added that one to my variable cost, then I'm going to get my total cost. Now the difference between the total revenue and the total cost is the profit. So profit is just revenue minus cost, right? So if they ask you to find the profit function when you are given the revenue as well as the cost, so all you need to do is to take the difference between the two. That is revenue minus the cost, and that gives us the profit, right? That is simple. Now remember here, the total cost here has a constant term here, which is 2,000. That is the fixed cost of production. It is the fixed cost of production. Now we're going to be doing this one when we deal with the theory of cost, when we study the theory of cost, probably in the third week. So this is the fixed cost, and the cost that varies with output is referred to as the variable cost, right? So we add this variable cost to the fixed cost to get what? The total cost. So if we take the difference between the revenue and the cost, then we're going to have the profit. So that is what we're going to do next. Okay? So let's move on. Now, from the model, profit of the farm is given by what? RQ minus CQ. I said revenue minus cost, right? So what we need to do now, we plug the revenue function and the cost function into the equation, and that gives us what? Pi q equals 1200 q minus 2q square, right? Minus, remember, we need to enclose the entire cost equation in brackets so that we don't mess up, with this negative sign, right? So we have q cubed minus 61.25 q squared plus 1528 q plus 2000, right? Everything in brackets. Now let's open the bracket. Now let's expand. What do we do here? Now we solve equation 2 by expanding this one, right? So if we expand this, we're going to have 1200 q minus 2q squared minus q raised to the power 3, right? Because this minus times plus is minus. And then minus times minus here, minus 61.25 becomes plus 61.25 q squared, right? And then minus times plus is minus 1528 q. And then minus times plus here becomes minus 2000, right? So if we solve that, we're going to have minus q cubed here plus, remember we have a minus 2q squared here. And then we have a plus 261.25 q squared. We bring all the like terms together. Q squared, they are similar, right? So minus 2q squared, remember this minus sign affects the negative sign in bracket, right? Becomes plus. Minus 2q squared plus 61.25 becomes plus 51.25 q squared, right? So plus 61.25 minus 2q squared becomes plus 59.25, right? And then we have what? We have 1200 q and then minus 1528 q becomes what? Minus 328.5 q. And then minus our 2000, right? Now, let us differentiate now. How do we do? That simple method I showed you earlier. You take this power, the power of the exponent here of q is 3, right? The exponent is 3. So multiply that exponent by a q, that becomes 3q, right? And then raise to the power 3 minus 1. Now we don't say again 3 minus 1, just say 3 minus 1 is 2, we write the value 2. Have you seen? So you have minus 3q squared plus, now we take this 2 and then we multiply it by 59.25, then we have 118.5. Have you seen? And then q, then we take 1 from this power, this exponent. 1 from 2 is just 1, right? So the q becomes q to the power 1. Got it? Q to the power 1. But we don't say q to the power 1 because q to the power 1 is the same as q, right? We just say q. Okay. Now let's come to this one. Now remember, want to differentiate 328.5 q. What do we do here? First, let's bring the negative sign. And now let's differentiate 328.5 q. Well, q is raised to the power 1, right? So we are going to take that exponent 1 multiplied by 328.5, and that gives us 328.5. Then q, now q raised to the power 1, 1 minus 1. We always have to subtract 1 from the exponent. 1 minus 1 is what? Is 0. So that's why I told you earlier that a variable raised to the power 0 is 1. You need to know that one. So because q has been reduced to what? Q raised to the power 0, that q to the power 0 becomes 1. And that 1 times 328.5 becomes that. Now remember, the derivative of a constant is always 0. Now, this 2000 is a constant. Did you see any q associated with that? No. So it is just a constant number. So if you differentiate y equals to y equals to 10, and then somebody has to find the y dx, it is just 0, right? It is just 0. So the derivative of a constant is just 0. So because the derivative of this 2000 is 0 with respect to q, it collapses. So we now have an equation for the derivative of pi with respect to q, giving us minus 3q squared plus 118.5q minus 328.5. So that is the derivative. That is simple. And this is what we're going to be doing. This is what we're going to be doing to find the optimal values. Find the optimal values. Find the points where the producer or the farm maximizes profits. Find the first order condition, the second order condition. Remember, this is the necessary condition for optimization. And then the sufficient condition for optimization is referred to as the second order condition. So that means we're gonna find the derivative of this first order derivative. That's why they call it the derivative of the derivative. D squared pi dt squared. So we have those conditions. So when we deal with optimization, we're going to study this one in detail. Let's move on. So I hope you understand. If you don't understand, please feel free to give me a call. Please feel free to give me a call. I want you guys to be on top of this one. I want you guys to know this one to your fingertips. You should know every details of this one. I want you to understand this very, very well. Because you're going to be doing this, you're going to be using this one to do your research, to do your semester paper. You're going to be doing some modeling as well as collect the data. And I'm going to post the writing prompt shortly. So let's move on. Now, we talk about the derivative of a constant, right? It is 0. The derivative of a constant function, y equals to f of x equals to k. K is a constant, it's always 0 for all values of x. Remember, this sign represents for all values. For all, it means for all, right? For all values of x. This implies that the differential of a constant function with respect to x is 0 for all values of x. So the y dx equals the f of x dx is equals to 0. It's a constant, right? It's a constant, so it is 0. You got it? So that's why I say if y equals to 2000, the y dx is just 0. Got it? Good. Let's move on. Now, we have the second rule, which says the sum rule of differentiation. Right? The derivative of the sum of two functions is simply what? The algebraic sum of the individual derivatives of the two functions. So, if we have the sum of two functions, right? Let's say, for example, we have f of x as 1 and then plus g of x, right? H of x equals to f of x plus g of x. So this represents the sum of two functions, right? Algebraic functions, right? So what we need to do is to find the derivative of each of them and then add them together. Basically, that is the sum rule of differentiation. It is called the sum rule of differentiation. In other words, it is called the addition rule of differentiation. So when you add two functions, just find the individual derivative of each of those functions and add them together. That is the rule. Okay? So if we have h of x equals to f of x plus g of x, then the h of x dx is given as what? df of x dx plus dg of x dx. So we find the f of x dx and then we find the g of x dx. We add those two together and that gives us the h of x dx. Okay? So let's try to make things simple now. Now we have f of x equals to 3x squared, 3x to the power 5 plus 6x to the power minus 2. Now remember, when we say x to the power minus 2 is what? This minus sign represents what? 1 over x, right? So that becomes 1 over x squared, okay? For those of you who don't know, so x to the power minus 2 is 1 over x squared, right? Okay. So that becomes 6 over x squared. It's the same as 6x to the minus 2. So we have these two functions, 3x to the 5 and then 6x to the minus 2. We added them together. So what we do here is what? We find the derivative of the first function 3x to the power 5 with respect to x. And then we do the same thing for 6x to the minus 2. Once we find those two, we added them together, and that gives us the f of x dx. Okay? So to solve it, we simply take the derivative of the individual functions and add the result together. Simple. Now, as I said earlier, that general rule, you don't have to forget that, right? You have 3x to the power 5. What do you do to this exponent? You take that exponent and multiply it by this whole 3x, right? And that gives us 5 times 3x is 15x, right? And you take 1 from that exponent. 5 minus 1 is what? 4, right? Simple. That's your derivative, 15x to the power 4. It is as easy as that, right? Now we take this minus 2. Now there is a twist here. Now we are not just going to take 2 here. We're going to take the whole exponent, which is minus 2. Don't just take 2 times 6. No, don't ever do that. You need to take the entire exponent, which is minus 2. You got it? So you take that minus 2, and then you multiply that by plus 6. That gives you what? Minus 12. Minus times plus is a minus, right? And remember, whenever you multiply two different signs, now when I say different signs here, you have plus and minus, the answer is always a negative. Whenever you multiply two similar signs, the signs are similar, negative, negative, the answer is always a positive, right? Whenever you divide again two different signs, when you multiply two different signs and then you divide two different signs, the answer is always a positive. Just have that one. The answer is always a plus. Okay? And then when you divide two similar signs, minus, minus, minus divided by minus, and then you multiply two similar signs, minus times minus, the answer is always a plus, right? Sorry. Oh, I think I messed up. Now, when you multiply two different signs, minus, plus, and then you divide two different signs, minus, plus, the answer is always negative, right? It's not a positive. I misspoke. So it's always a negative. So whenever you divide two different signs, plus, minus, or minus, plus, you multiply two different signs, minus, plus, plus, minus, the answer is always a negative. It's always a minus. Okay? Whenever you multiply two similar signs, minus times minus, divide two similar signs, minus divided by minus, or maybe plus divided by plus, plus times plus, the answer is always a positive. You understand? Okay, so always have that in your head. So I multiply two similar signs, it's positive. I divide two similar signs, positive. Then when I divide and multiply two different signs, is what? Is always a negative. Don't mix those things up, right? Different signs, negative. Similar signs, positive. If you have that, I think you'll find this thing so easy, right? So this is not rocket science. I'm telling you, this is not rocket science. If only you're able to do this, you can do whatever things you want to do in economics. It's not rocket science, okay? So minus 2 times plus 6, that gives us minus 12. And then again, I told you have to subtract 1 from the exponent. Now I'm going to take minus 1 from minus 2. Minus 1 minus 2 minus 1 is minus 3. Okay? Minus 2 minus negative 2, negative 1 is negative 3. So it's just like saying 2 plus 1 is 3, okay? So negative 2, negative 1 is just negative 3, okay? And then negative 2 plus 1, that's a twist, right? Negative 2 plus 1 is what? It's negative 1. Because in math, the greater number carries the sign. The 2 is bigger than the 1. Because it has a negative sign, so the answer should be negative, okay? So negative 2 plus 1 is just minus 1, okay? And then negative 2 plus 3. Now remember the plus 3, the number 3 is bigger than the 2, right? It has a positive sign. Just take the difference between the two and then you put the positive sign, plus 1, okay? So negative 2 plus 3 is what? Just say 3 minus that. And that gives you 1, right? Negative 2 plus 4, just say 4 minus 2. That gives you 2. Positive 2, right? So simple. Okay, so now we have negative 2 minus 1. That gives us negative 3. And then we have 15x to the power 4 minus 15 minus 12x to the power minus 3. So this is the derivative. You can simplify this further if you want by just factorizing. Check the common factor here. The common factor is 3, right? Because 3 can go into 15, it can also go into 12. And that is what? 3, 15 divided by 3, you see 3 into 5x to the power 4. And then, so we say what? Here, say 3 is common. 3 is common, right? So 3 brackets 5 x to the power 4 and then minus, now 12 divided by 3 is just 4 x to the minus 3, right? So we have 3 into 5x to the 4 minus 4x to the minus 3. So that is that's the answer, right? So when you simplify, so that's the answer, okay? Okay, let's move on. So now let's look at the difference rule here. Now, just as we say the sum rule, if you differentiate the sum of two functions, just find the individual derivatives and then add them. We do the same thing here. If you subtract two functions, then the derivative of that difference with respect to x is just the difference of the individual derivatives. Okay. Now let's say, for example, we have y equals to f of x equals to 4x to the power 3 minus 3x to the power 4. Now 4x to the power 3 is one function, and then minus 3x to the power 4 is another function, right? So we take the difference between the two. So what do we do here? We differentiate the first function with respect to x, that is 4x to the power 3. What do? We take the exponent and multiply by 4x, that gives us 12x, right? And then we subtract 1 from that power, that gives us what? 2. Or 3 minus 1 is 2. We're done with that. Now we'll put our negative sign, minus sign. Let's come to the next function. We differentiate this 3x to the power 4 with respect to x. What do? We take 4, which is the exponent. We'll multiply by 3 again. It's 12, right? 3 times 4. And then x. Then we subtract 1 from the 4. And then 4 minus 1 gives us 3. We have x to the power 3. So now we have 12x to the power 2. And then we have minus 12x to the power 3. Now, we take 1 common. We can factorize this further. We take 1 factor here. Now, remember, 12x squared is common. 12x squared is common. We take 12x squared out. Now, if we factorize, we're going to have 1 minus x, right? Now, just say 12x squared divided by 12x squared is 1, right? And then 12x to the power 3 divided by 12x squared is just x. 12 and the 12 cancel, the x squared. Remember, x to the power 3 divided by x to the power 2 is what? The laws of basic indices is x to the power 3 minus 1, right? Minus 2, right? X to the power 3 minus 2, right? A to the power x divided by a to the power y is a to the power x minus y, right? Basic indices. I know you've done this one in your high school algebra. Now, let's move on to the product rule. Now, the derivative of a product rule of two functions is the derivative of the second function multiplied by the first function plus the derivative of the first function multiplied by the second function. Now, this is the rule. You need to know this one, right? You take the product of two functions, right? Is the derivative of the product of two functions is the derivative of the second function. That means you're going to take, if you have y equals to u of x plus v of x. First, you are going to take the derivative of the second function and then you multiply by the first function. That's the first thing you have to do. And then plus, you take the derivative of O. So it's a twist here. Now, we don't have a plus here. This one should be u of x multiplied by v of x, right? So I think this was a typographical error. This was a typographical error. It should not be plus. It should be u of x multiplied v of x. There is no plus here, please. No plus here. No plus. This one is off. It's off. Okay, this is multiplied. Okay, so u of x multiplied by v of x, right? So take out the plus. F of x, y equals to f of x equals to u of x multiplied by v of x, right? So then the derivative of y with respect to x is given by what? This second derivative, that is the v x dx multiplied by u of x, and then we take the derivative of the first function by what? The second function. That is the ux dx multiplied by v of x, right? So that is the rule. So now let's take one typical example. Now we have find the derivatives of the following: y equals to 6x cubed minus 4, then multiply by 4x squared plus 3x, right? So what do we do here? It is simple. Now the second term here in bracket 4x squared plus 3x is what we're going to differentiate first. And then we'll multiply that result by the first term, right? And then we'll do the same thing again to what? The derivative of the first term, and then we'll multiply by the second term. Then we add the two. Okay? As simple as that. Now let's move on. Now we have the first term and the second term here. So what we do here is we're gonna take the derivative of 4x squared plus 3x first, which is what? The 4x squared plus 3x dx multiplied by what? 6x cubed minus 4. And then plus 4x squared plus 3x multiplied by the 6x cubed minus 4dx, right? The derivative of the second function, or the first function. Now let us differentiate this second term. Again, what do we do here? We take this 2 by 4 is 8, and then we'll subtract 1 from that 2, that gives us 8x, right? Plus 3x is 1 times 3, which is 3, and then x to the 1 minus 1 is just 0. So x to the 0 is 1. 1 times 3 is 3. So this term in brackets is derivative of the second term, and then multiply by the first term, which is 6x cubed minus 4, right? Plus, now we have 4x to the power 2 plus 3x, which is the second term. Now let us find the derivative of the first term. What do we do here? We take 3 times 6, which is what? 3 times 6 is what? Oh man, this one should be 18. 18. 3 times 6 is 18. Oh man, this is not. Oh, this is 18, right? 18x 3 by another 18x to the power 2, right? And then 18x to the power 2, not 12, okay? And then the derivative of this constant 4 is just what? It's just 0. The derivative of a constant 4 is just 0, right? So we have that. Multiply this by that. Then if we expand this, we're going to have this first term, and then minus minus 12, yes, right? If we expand this, we're going to have this plus 12, 18 times 4. 18 times 4, oh, this is not correct. This one should be 72, right? 72. Okay. That should be 72x to the power 4, right? And then you have 18 times 3 is 54. That is not correct. Yeah, this should be 5 and 4. Okay. 54x to the power 3, not 36, okay? It has to be 54x to the power 3. So you change that. That 54x to the power 3. So you solve that. Of course, this one should be redundant. This one is not correct. So make sure you do the math. This one should be 72 x to the 4 plus 48 x. 72 plus 48 x to the 4, that's going to give us what? That's going to give us 120 x to the 4, right? Yes. And let's look at this. 18x to the 3 plus 30 plus 54x to the power that. So 6 plus. That's gonna give us 72, right? Instead of that, x to the power 3. And then minus 32x, and then minus 12, right? There you go. So this is the correct answer, not this one, okay? So let's move on. Now we move on to the quotient rule. Now for the quotient rule, you have the derivative of the quotient of two functions f of x over g of x is what? Is just f prime x gx minus f of x by g prime x. Now, you know what g prime x is? G prime x means the derivative of g of x with respect to x, okay? So I just shut it out. You're going to be seeing this one quite often. F prime x is the derivative of the numerator multiplied by denominator minus the numerator multiplied by the derivative of the denominator divided by the denominator square, okay? That is g square x, okay? So now let's find derivative of this. Y equals to f of x equals to x squared minus 3 divided by x. Now, first, we're going to find the derivative of the numerator, which is what? We differentiate the top, the numerator. That gives us 2 times x, and then 2 minus 1 is just 1, so it's 2x, right? Multiply by my denominator, which is x, minus what? The derivative of the denominator, which is 1, because y equals to x, the y dx is just 1, right? The power of x here is 1. 1 times x is x, and then 1 minus 1 is just 0. So x to the power 0 becomes 1, which is this one, right? Multiply by the numerator x squared minus 3, and then we divide everything by the square of the denominator, which is x squared, right? So if we expand this one, we're going to have this term. Solve that one when you go home, okay? Now let's look at the chain rule of differentiation. Now, the chain rule states that if w equals to f of q, it's a differentiable function of q, and q in turn is a differentiable function of another variable x, then the derivative of w with respect to x is the product of the w, the q, and the q, the x, right? So if w equals f of q and q equals f of x, then the w, the x is given by what? The w, the x is the w, the q the x, right? Now suppose we have z equals to a squared and y equals to dx squared plus 2x, right? Then the z, the x, is equals to what? The z dy multiplied by the y dx, right? The z dy multiplied by the y dx. Thus, the z dx equals to what? 2ay, right? Into 2dx plus c. Since y equals to bx squared plus cx, follow that this one equals to that. Then if you expand, you're going to have this, okay? Now, let's look at derivative of transcendental functions. Now I told you we have the exponential function and the logarithmic function, right, as transcendental function. So if y equals to e to the ax, where y is a function of x, the derivative of this exponential function with respect to x is just what? ae to the ax. That's it. It's ae to the x, right? Y dx is just ae to the x. You just take the coefficient of x, right? You multiply by the whole term, and that's your derivative. That one is so simple and straightforward. Now, for logarithmic function, y equals to ln x, then the y dx is just 1 over x. Just take the reciprocal of x. That is the derivative, okay?